So, I should say, it's my pleasure to introduce Mehrdad Kalantar from University of Houston. His title is First Singular Boundary of a Discrete Quantum Group. So, please.
Thank you. Okay, thanks everybody. Very nice to see you all here. Thanks for the invite. And okay, I don't, right, okay. I'm very glad to speak here today. Okay, I don't see the chat box, so if you have any questions, please please just jump in and stop me at any time. Okay, so I'm going to talk about a joint work of mine with Pavel Kasprzak and Adam Skolsky and Roland Vernieu on the notion of Furstenberg boundary for discrete quantum groups. I know there are definitely some experts on quantum groups here, but I'm not going to assume that everybody knows or have had experience with them. So I'm going to begin with very briefly tell you what quantum groups are. Particularly, we are interested in, as the name says, topological quantum groups. So this is okay. So this is a rather technical concept. I don't mean to go into the details of definitions and constructions. I just want to give you an idea of what objects are these, where do they come from, or at least how do we see them. So these are, in a sense, natural generalizations of natural generalizations of groups and specific.
Sorry to interrupt you, Mehrdad, but is there any way you can make your screen a bit brighter? It just looks a little dark.
Is it? Is it still dark?
Well, at least the text is quite bright, so I guess that's okay then.
I don't think it's on my side. I can do anything about it. Am I right, or do you know how could I do that? I mean, if I just make my screen brighter, I don't think it should change yours.
That probably won't have an effect. But actually, now that we can see the text, actually, I think it's probably okay because the text is quite bright, but it's just the background looks a bit dark.
Aha. Okay.
So I think it's okay. Sorry about that.
No, that's right. That's all right. So this is supposed to be my blackboard, and I'm writing with a white chalk on my blackboard. So sorry if the choice of colors were not so good. So I guess my head titles are black on a blackboard, so that's probably not good. But the text would be all white. Okay, good. So. Yes, I was saying that these are natural generalization in certain sense of topological groups. And so what's going to happen, so discrete quantum groups are going to be, are indeed certain generalizations of discrete groups. And we are going to be interested in certain questions, certain problems about these more generalized objects, questions about the C-star algebras, certain questions that at least we now know better about them in the discrete group case. Okay, so there are various ways to go about motivating where do these objects come from, but perhaps the most familiar for at least such a group would be. So you see, the word quantum here comes the same as a lot of us use the word non-commutative in other places. So let me just be a little bit now more, at least concrete. So we used to say, we always say that C-star algebras are non-commutative topological spaces, or quantum. Let me be consistent with the word quantum here. We say they are quantum topological spaces, and we have a very specific sense in mind. In fact, in the following sense. So there is a one-to-one correspondence between locally compact spaces and commutative C-star algebras by assigning to every locally compact space X the C-star algebra of continuous functions vanishing at infinity on X. And so what happens here, we can list a bunch of properties that if an algebra has them, then it would be the algebra, in fact, algebra of continuous functions, the algebra C0 on a locally compact space X. And we can recover X from that in a unique way. And then you list all those, which are just being a commutative C-star algebra, and then you drop the word commutative, and that's what we call, well, that's our C-star algebras, and that's how they become, for us, quantum topological spaces. A similar way, we say von Neumann algebras are quantum measure spaces. Again, there is a one-to-one correspondence. So here, let me assume all the spaces are nice, all measure spaces are sigma finite, etc. The ones that I'll be interested in. So in that case, you know that I can assign to any measure space X and mu the von Neumann algebra of essentially bounded functions on that, measurable functions on that, and that gives me a way to make a one-to-one correspondence between measure spaces and certain von Neumann algebras, namely exactly the commutative ones, and you drop the word commutative. That's your quantum measure spaces. So in this sense, what would be quantum groups? So of course, I'm not interested in general algebraic, say, quantum groups. We are interested in topological quantum groups, and we all know that there is a huge difference between the theory of locally compact groups and non-locally compact groups. Namely, the existence of the Hall measure is the big difference. So I'm going to do the following. So given a locally compact group, of course, I can see it as a locally compact space. So in particular, I'm going to get a commutative C-star algebra out of this, C0 of the group. Question, what are the conditions that I need to add to a commutative C-star algebra in order to make sure that it is in fact C0 of a locally compact group, not only a locally compact space? So you just list those conditions, add those conditions to a commutative C-star algebra, and make a one-to-one correspondence between locally compact groups and certain commutative C-star algebras, and then drop the commutativity from those conditions, and that would be your quantum locally compact groups, or as we say, locally compact quantum groups in C-star algebra setup. But as I said, so there is a very distinguished feature of locally compact groups, the existence of Hall measure. And in fact, the topological structure and measure theoretical structure coming from the Hall measure, they really determine each other in a unique way. So every locally compact group has a unique Hall measure, and other nice conditions, if you have a group with an invariant measure, then there is a unique locally compact topology that makes it a locally compact group. Okay, so that tells me that I can go both setting C-star or von Neumann algebra setting and do what I want to do, find the conditions, characterize them, and drop the word commutativity. So I can pick C0 of G or L infinity of G as my function algebra that I want to work with. And in fact, you can go either way, and there will be two parallel and equivalent theories. So you can recover one from the other. So let me just very quickly mention how we do it, for instance, in the von Neumann algebra setup. So to given a locally compact group G, let me assign to that an infinity of G, and this is with respect to the Haar measure. Then you want to, so then group structure adds certain things to this an infinity algebra. It's not just a measure space, it's the group. So in particular, a group comes with a product. And the product is just, you can see it as a map, and you can see this assignment as a functor sending G, an object in the category of groups, to an object in the category of, I don't know, commutative von Neumann algebras. And so maps here, see them as morphisms, will canonically be translated to morphisms on the other side. Right, the product, I see it as a map from G cross G to G. That translates to a map from an infinity of G to an infinity of G cross G, which is the same as an infinity of G tensor product, von Neumann tensor product, and infinity of G. Then the product is associative, so you're going to get, just translate the associativity via this functor. That would translate exactly to this relation, which we call co-associativity of the map. And then, of course, you need an inverse, but so the inverse is more subtle. Actually, this was the source of a lot of issues that kept this theory to not come out perfectly nice. So it turns out that you really have to change the inverse with cancellation laws and existence of invariant, well, say existence of Haar measures. Okay, I don't mean to go into the details of why and how and etc. So having that in mind, let me just give you very quickly the definition that is now mostly accepted, the most elegant definition that exists. And you see that from here that one can go different ways about doing this. So obviously there might be different ways of defining or quantizing groups, but the most accepted one by now is due to Kustam and Was, and goes as follows. And I'll do that in the von Neumann algebra setup. A locally compact quantum group is a quadruple consisting of a von Neumann algebra M, which is supposed to be my L infinity, a coproduct delta, we call it a coproduct or co-multiplication, which is a normal unitary isometric star homomorphism, and it's co-associative as I just mentioned in the last page. And we also assume existence of Haar integrals. So these are going to be NSF weights on the von Neumann algebra satisfying an invariance condition. And if you just sit down and write the invariance of Haar measures, when you translate everything in the L infinity setting, then this would be the exact formula for that. And also assume existence of a right invariant Haar measure, Haar integral. That would be an NSF weight on the von Neumann algebra satisfying this right invariance condition. And so this is the definition of a locally compact quantum group. If M happens to be a commutative von Neumann algebra, then M with these extra structure will indeed be an infinity of a locally compact group, a unique locally compact group, where delta and others are as follows. So let me.
Sorry, Mehrdad, can I just ask a quick question? What is the M sub star and M sub plus?
Oh. Substar would be the pre-dual all the time. I'll use that in other places. Actually, that's a good point. So it's more appropriate to say that this equation holds for all x, where phi, all positive x on which phi is finite, and so one has to show that if x is in the domain of phi, I mean it's a positive on which phi is finite, then this guy would be also in the domain, and this would be a finite, a positive element on which phi is finite for any normal linear functional. I shouldn't say this is, okay, so here I should say, perhaps I should say normal state to begin with. But then, yes. Go ahead.
So then omega tensor ID acting on the coproduct of x will actually land inside an M, and then phi operates on that, and you land inside an M.
Yes. Yes. That's right.
Yeah. Okay. Great.
Yeah.
Thank you. Thank you.
Of course. Okay. So examples, commutative locally compact quantum groups are nothing but locally compact groups in the following sense. Given a locally compact group G, you can form the quadruple L infinity of G delta phi psi, where delta, so this is supposed to be a map from L infinity of G to L infinity of G tensor L infinity of G, which is the same as L infinity of G cross G. And this is the canonical functorial map that I described on the first page, I guess. And phi and psi will be just left and right Haar integrals or Haar measures. And every locally compact quantum groups, as defined in the previous page, for which the von Neumann algebra is commutative, is indeed this one. And the so-called co-commutative comes from the group von Neumann algebra. So again, G is a locally compact group. L of G is the group von Neumann algebra. This is the von Neumann algebra generated by all left regular representations of group elements inside B of L2 of G, where the coproduct is defined. So this von Neumann algebra is generated by these elements. This is the left regular representation of a group element S. And phi and psi are the same in this case. They are the Plancher weight. So what I guess, let's take this with us, that if G is discrete, in that case, phi and psi are equal, and they are nothing but the canonical trace on the group von Neumann algebra of the discrete group, which is just a vector state corresponding to the vector delta E, the Dirac function at the neutral element, seen as a vector in L2, little L2 of the discrete group. So that in that case, you get a nice faithful trace, and that's going to be the Haar integration for us. Again, there were different motivations to introduce or develop these theories coming from different angles. But one of the angles, so purely mathematical angle to this, so there were mathematical physics motivations to study these structures. But a mathematical angle to be motivated to look at such structures come from the problem of extending Pontryagin duality to non-abelian groups. So given any abelian locally compact group, there is naturally or canonically a dual group assigned to it, which is itself a locally compact abelian group. And you have a biduality, Pontryagin biduality, that if I take the dual of a dual, I'm going back to my original group. And that's the whole, let's say, foundation of Fourier analysis. So if my group is a group of circles, then the dual would be Z. And in fact, a nice function on the circle, the Fourier transform is going to be a function on Z. But if you look at it, and look at the definitions, it's basically a function. So the Fourier transform of a function on a locally compact abelian group is indeed a function on its dual. And so, of course, it's very natural to want to have a Fourier analysis. There's no need to say how important Fourier analysis is, to have that for non-abelian, perhaps, groups. So it turns out that you cannot have a nice perfect duality theory within, for all locally compact groups, but within the category of locally compact groups. So it turned out that somehow you have to embed the category of locally compact groups into a bigger category, and then there perhaps you can have a duality, which still you want to extend the duality of locally compact abelian groups. And this bigger category turns out to be the category of locally compact quantum groups. So to each locally compact group G, one can assign in a canonical way a locally compact quantum group G hat. It's dual, and there is a perfect biduality that if you take dual, you go back to your original group. So in the von Neumann algebra setting, by the way, I already mentioned one can define locally compact quantum groups entirely in C-star algebra setting, and one can get one from the other. There is no, so the theories are quite parallel. The dual of the quantum group LG, as we defined in previous page, at infinity, the dual of commutative ones would be what we define the co-commutative ones. And already here you see that in the abelian locally compact group case, this will be the usual duality, Pontryagin duality, because if G is abelian, L of G is canonically identified with L infinity of G hat, its Pontryagin dual. And in C-star algebra setting, the dual of C0 of G as a quantum group with all its structures is the reduced group C-star algebra of G with similar quantum group structure as L of G that we define. Okay, so you see, we are going to be interested in the case that G is, so when G is discrete, this C-star algebra becomes a nice unital C-star algebra, and certain questions about this C-star algebra is the motivation for this work. Certain questions that we know the answer for in the case of discrete groups, but we want to now look at those questions in the case of discrete quantum groups about exactly this object. Okay, so but
sorry, may I ask a
yes,
question?
Of course.
Like, can you go back to the previous slide?
Yes.
So I'm like, so classically, like you would encounter, I guess, like something like C-star reduced of, say, an abelian group would be like C, at least like without the extra group structure, isomorphic to C0 of G hat itself, right?
Yes.
And so how does this generalize? So I'm like passing the G, the hat inside.
Yes, hat goes inside, this becomes, so if G is abelian locally compact group, this would be canonically via the Fourier transform, this would be C0 of G hat.
Mm-hmm. So is there some more general relation?
In what sense? Sorry.
Like, I don't know, whenever G, like whenever a quantum group arises as a classical group?
Oh, so you see that, so you see this is commutative if and only if G itself is abelian. So, so the dual of commutative ones are co-commutative ones. The dual of co-commutative ones are commutative ones. And that's it. So they are closed under this. So there is no other quantum group whose dual or itself gives you a commutative or co-commutative object, if I understood your question.
But if it's not commutative,
so
like it still may be classical, right?
No, you cannot. I mean, so either, so you see there are two sides to this. So if the C-star algebra itself is not commutative, then of course you are not such thing, but you may be this thing. So if you are not a commutative C-star algebra and the coproduct is not symmetric, then you are not in the classical case for sure. So you are somehow in the classical either on this side or that side, if and only if either the C-star algebra is commutative or the coproduct is symmetric. So the coproduct delta of any element lies in the tensor product. We say it's symmetric. If I flip, I get the same thing. If I compose the coproduct with the flip operation on the tensor product, it doesn't change. So you can completely characterize the commutative setup. Outside of that, you are not commutative.
Or maybe put differently, like so if the dual is classical,
yeah,
is the original quantum group necessarily honestly quantum? So can it not be classical?
Yeah, I mean, so look at this. So you see this C-star reduced of G, its dual will be C0 of G by duality.
Mm-hmm.
So this is not commutative, but its dual is commutative.
I mean, like drop commutativity aside, but I mean, like just a question about being classical or quantum or honest quantum.
So by classical, you mean, do you mean, so classical for us means that it comes from a locally compact group. Yes. So classical means either you're this or you're this. Or, so if you mean something else from classical, then.
So C-star reduced of G, this is like a classical group, right?
Yes.
And then the dual, will it necessarily be quantum?
The dual of a quantum group is a quantum group, but the dual will be
not
C0.
Classical. So will it?
No, it will be classical. It has to be.
The dual of a classical group is always classical itself.
So look, so it really you really have to say what classical means. So to each group, let me say this, to each group, locally compact group, they're assigned two different quantum groups, which I defined here, the commutative and the co-commutative. Mm-hmm. So if you start from a commutative case, its dual will be this one, the co-commutative one. And if you start from the co-commutative one, then the dual will be the corresponding commutative one. So these two are the dual to each other. And these are the ones that we call classical. So the dual of a classical is a classical, but in this sense, the commutative one will be the co-commutative and vice versa.
So C-star reduced or L infinite or LG corresponds to the first one, and the yes. second one corresponds to, is there some other, like some other C-star, phenomenal algebra that one usually, I mean, like the first one is like the reduced phenomenon, the phenomenal group phenomenon, right?
Yes.
And the second one, is it better known under another name?
What do you mean by second here?
Yes. So is it maybe known under another name?
So they are called co-commutative. So this L of G is the group form. Yeah, these are called co-commutative because, so I mean, these are the ones that the coproduct, as I say, are symmetric. So if you do the flip, it doesn't change. So commutative and co-commutative, this is how we call them. These are the classical versions.
Okay. Yeah. Sorry. Thanks.
No, of course. Okay. Right. But so this was locally compact quantum groups. What are the discrete or the compact ones, the ones that we are interested in? So the discrete, so I mean, exactly natural definition that you would expect. So a locally compact group, let me remind you that it's discrete. You can define it in different ways. But one way is to say that the L1 algebra with the convolution is unital. And let me just take that definition, but you can do others. So we call it quantum group discrete. And please note that the von Neumann algebra here, so this co-multiplication, as I said, it's a normal map. So if I take the pre-adjoint, it's going to give you a product, in fact, on the pre-dual of the von Neumann algebra. It makes it a Banach algebra. This is indeed, in the commutative case, the pre-adjoint of the co-multiplication is nothing but the convolution product on L1. So we say quantum group is discrete exactly when that Banach algebra is unital. We say quantum group is compact if the quantum version of the Haar integral is finite. So that's exactly saying a locally compact group is compact if and only if the Haar measure is finite. And just like the classical case, we do have a quantum group is discrete if and only if its dual is compact. So in a sense, so the reduced group C-star algebra of a discrete group is in fact the C-star algebra of a compact quantum group. So it's its dual, right? So it's a dual of a discrete quantum group, or in this case is group, it's going to be a compact quantum group. And I should say that in practice, the examples, the interesting examples that are constructed are mostly constructed as compact quantum groups. And so the discrete quantum groups that the ones that we study here, or the ones that appear most naturally in practice, they are constructed as duals of certain compact quantum groups. Okay, so so we are going to be focusing on discrete quantum groups for the rest of the talk. This bold gamma denotes a discrete quantum group. In this case, we know that the von Neumann algebra of the quantum group, I'm going to use the notation little at infinity for that, to just be similar to the classical case. But please understand that there is no, so this is not an underlying set. This is just a notation to denote the von Neumann algebra of the quantum group. In that case, the von Neumann algebra of the quantum group is an infinity direct sum of finite dimensional matrix algebras. So this would be commutative exactly when all of these are one dimensional. And that's your classical case. And so what you wonder, what would be the Haar integration in this case? You do have a very canonical candidate, and that would be the direct sum of traces. But in fact, that's not always invariant in the sense that we wanted with respect to the co-multiplication that exists here in all examples. That would not be the Haar integration, Haar weight. But if that is the case, then we say the quantum group is unimodular or of Cutts type. And that would be equivalent to having the Haar weight on the dual quantum group to be a trace. Now, notice that the dual quantum group would be compact, so the Haar weight is finite, so it's a Haar state. Traciality of that is equivalent to this unimodularity condition, which means that the direct sum of traces here is exactly the Haar state. So in this case, everything is more manageable. Objects are quite nice. Okay, good. So let me get into this notion, but before I get into introducing the Furstenberg boundary of quantum groups, let me tell you what is the motivation for this. Okay, so this was motivated by certain recent applications of the notion of Furstenberg boundary in C-star algebras of discrete groups. So let me quickly.
Sir, Mehrdad.
Yes.
Can I ask a quick question? So the Cutts type you said that discrete locally compact quantum groups are going to be dual to compact quantum groups. So then the Cutts type, I guess, it's Cutts, and one is Cutts, the dual is Cutts.
Yes, exactly.
Okay, great. Thank you.
Yes. Okay, so I'm going to go quickly over these problems that really were the reason we started to look at this concept. So these are the questions that were there for discrete groups and were answered using this notion of Furstenberg boundary. And then, of course, these questions were all there for quantum groups, and we wanted to attack them. So obviously, naturally, we were led to developing this notion in the quantum case. So first problem was the problem of nuclear embeddings of exact C-star algebras, and second, C-star simplicity, and the third was the problem of uniqueness of traces. So let me go over them very quickly. What is this question? So I'm going to recall the definitions of nuclearity and exactness, but in a different way than the original definition so that it suits my purpose here. So a C-star algebra is nuclear if there are UCP maps, phi I and psi I, as you see, going from A to finite dimensional matrix algebras and the other way around, such that when I compose them, they would converge to the identity operator on A and point norm topology. And we say a C-star algebra is exact if you have a similar if you have a similar situation where now you relax the condition on the second maps, you allow them to go into maybe a larger C-star algebra that contains A, but still you want the composition to go to identity map in point norm topology. Now you see obviously that with these definitions, if I am a subalgebra of a nuclear C-star algebra, then I am exact. And the converse is true. It's a rather deeper result. But the problem here is, okay, if I start from an exact C-star algebra, how do I find a concrete and nice canonical meaningful embedding into a larger nuclear C-star algebra? So this statement here that I say the converse is true is an existential say. I mean, there is one nuclear C-star algebra that contains all separable exact C-star algebras. So this result is not very constructive and canonical. So in particular, Ozawa conjectured the following. He conjectured that given an exact C-star algebra, well, I mean, he formulated for separable exact C-star algebras A, there must exist a nuclear C-star algebra B such that B lies between A and its injective envelope. So this is the injective envelope of A that is the minimal injective C-star algebra that contains A. So why is that good if you have it? The point is A and its injective envelope, or the objects in between, they do share certain structural properties. For instance, if A is simple, then B must be simple. If A is prime, then B is prime, etc. So then this is meaningful. Then there are certain things that you can deduce from one to the other. So he answered, well, he proved the following, that this is true for the reduced group C-star algebra of the free group, where in his proof, the nuclear C-star algebra B appears to be the reduced cross product with the continuous functions on the Gromov boundary of the free group. With Matt Kennedy, we generalized that to all exact groups, to all reduced group C-star algebras of discrete groups when they are exact. We proved his conjecture, where for us, B appears to be the reduced cross product with continuous functions on this so-called Furstenberg boundary. I'll define it in few slides, but I just want you to see that it appears in the answers. Ozawa's conjecture remains open in general. That's the best general result that exists for reduced C-star algebras of exact groups. The second, C-star simplicity problem. So the question, the problem is for which groups gamma, discrete groups gamma, the reduced C-star algebra is simple. Can you characterize them? So this goes back to a result of Powers from 70s, where he showed reduced C-star algebra of the free group is simple. And there has been tons of results after that, but the characterization was missing. And again, in the same paper with Matt Kennedy, we did prove that reduced group C-star algebra is simple if and only if the action of the group on this Furstenberg boundary, which I yet to define for you, but it's a compact space on which gamma acts, is free. So again, the dynamics of this appeared in the answer. And the third question, which I wanted to look at, was the question of for which groups gamma the reduced group C-star algebra has a unique trace. And again, in the answer, which was in our work with Brouillard, Kennedy, and Ozawa, we proved that the reduced group C-star algebra has a unique trace, which is just a canonical trace, if and only if the action on the Furstenberg boundary, action of the group, is faithful, meaning that the kernel of the action is trivial. So again, this Furstenberg boundary was the key to answer all these questions, and so more or less this closed this whole set of problems. All the questions above are relevant, very well formulated, interesting and important in the quantum case, and more or less not much known about them. There are some ad hoc results about C-star simplicity and unique trace, and Ozawa's conjecture, of course, more or less nothing before this work of us. So the goal here is to extend the notion of Furstenberg boundary to the quantum case and apply it to these problems. Okay, so let me proceed with giving you the definition of Furstenberg boundary for groups, the commutative case, the classical case, and then we see how it naturally generalizes or extends to the quantum case. So the definition, as the name suggests, goes back to Furstenberg from 60s. So an action of a discrete group gamma, this is defined for locally compact groups, but here our focus is on discrete groups. An action on a compact Hausdorff space X by homeomorphisms is called a boundary action if the following happens. If the orbit of any probability, so for any new Borel probability on X, if I look at its orbit under the action of gamma, then its convex Hall inside probabilities of X is weak star dense. Actually, sorry, this must be X. Yeah, this is a typo. So the weak star closed convex Hall of the orbit of nu is the set of all probabilities, which is the same as saying that the weak star closure of the orbit of nu must contain all the delta measures. Equivalently, something that we could use is that an action is a boundary action in the above sense if and only if the so-called Poisson transform is isometric. A Poisson transform is a transformation of functions on X to functions on gamma in the most natural way. So given new probability, you can evaluate, you can integrate, if you like, a function along the translates of nu, and that gives you a function on gamma. And such map is very naturally defined in the, so you see here, all I need is sort of a convolution product type thing to define such a map. Okay, but Furstenberg showed that among all these boundary actions, there's always, given any gamma, there's always a universal such action. Now we call it a Furstenberg boundary. Universal in the sense that all others are continuous equivalent image of this universal one. Or continuous functions on X would embed to continuous function of this universal one. We proved with Kennedy that the continuous functions on the Furstenberg boundary is canonically identified with this object, so-called the gamma injective envelope of C. So what is this? This is the minimal injective object in the category of all gamma C-star algebras where morphisms are unital UCP maps, which are also gamma equivariant. In that category, Hamana proved that there is always a minimal injective object, and that's what we denote by this. And so this identification was, at least for us in that first paper, the key to translate these problems into the dynamics of this action and then go from there. Okay, so back to discrete quantum groups. So I want to extend this notion to the quantum case. So first, let me quickly mention these notions of action of discrete quantum groups and the objects here involved. A left action, I mean, it's the same sort of point of view. So action of a group on a compact set, how do I see it? As a map from G or gamma cross X into X. And then via this functor, it gives me a map from continuous functions on X to continuous functions on gamma cross X. And this is how you just extend that definition. So a left action is an injective morphism from A to multiply algebra of C0 of gamma. And this C0 is just the C0 direct sum of the corresponding matrix algebras. Well, this is the associativity condition translated in this language, associativity of the action. This one is less transparent, but you may consider this as the continuity condition of the action. So the continuity translates to this. In this case, we say A is a gamma C-star algebra, and all C-star algebras that I'm talking about here are unital C-star, or assumed to be unital. So the convolutions are all defined naturally. So the convolution, so you see, if I take this alpha and I take the adjoint of that, then it would give me a map from the dual of this into the dual of that. And so it gives me a way to define a module action of the dual of this C-star algebra on the dual of this C-star algebra. And that's nothing but convolving a measure on gamma with a measure on X in the commutative case. Okay, so there was something about faithfulness of the action. So in the quantum case, one has to sit and work a little bit with these objects, and you could come up with the following definition of a kernel of an action and faithfulness of the action. So perhaps I should move quickly from here, but there is a way to define faithfulness for actions of quantum groups, which would be the same as faithfulness, in the usual faithfulness in the commutative case. And equivariance of maps is defined the same in the quantum case. Note that for a discrete group action, a map between gamma spaces, whether really spaces or C-star algebras or von Neumann algebras are equivariant if and only if they are module maps with respect to the modular structure, module action of L1 of the discrete group. So you notice that when gamma acts on anything, then L1 of gamma acts on that thing, and that's our convolution map. And you are in the discrete case, and you are equivariant with respect to the action of gamma if and only if you are a module map with respect to the module action of L1. And when you go to the quantum case, you want to get rid of all points, and you want to stick to function algebras like L1 and infinity C0. Okay, the cross product, when I have an action of a quantum group on a unital C-star algebra, there is a notion of reduced cross product, and that is defined more or less the same. Again, very naturally generalizes the cross product construction in the group case. So all I want to say that these objects exist naturally in the quantum setting. We are not defining them, they did exist, so they have been studied very well. And so, so all the pieces exist to naturally generalize the notion of boundary actions. So the definition goes as follows: given a gamma C-star algebra A, we call it a gamma boundary if the following set, the set of all, when I take a state, a normal state on L infinity of my quantum group, and I convolve it with a state on the C-star algebra, then I get a weak star dense subset of the state space of A. That's just translating that the orbit closure of every probability is weak star dense in probabilities on X. And then one could show that characterize all gamma boundaries as is a gamma boundary if and only if every UCP gamma equivariant map going out of A into the von Neumann algebra of the quantum group is completely isometric, or any gamma equivariant UCP map going out of A into any gamma C-star algebra B is completely isometric. So this is like the Poisson transforms all being isometric. And we could prove that, and all these now, so from here on, everything
Sorry,
is, yes.
Can I ask a question? Like,
Yes, yes.
So how do we define L1 gamma for gamma, not necessarily, so for gamma a discrete quantum group?
So this is my notation for the pre-dual of L infinity of gamma. Sorry, thanks. That I forgot to mention. So this is my notation for the pre-dual of the von Neumann algebra with the convolution, the pre-adjoint of the delta, the co-product, which gives it a Banach algebra structure.
So just a normal state.
Sorry again?
So
these are
just a
normal states. Yes, yes.
Okay, thanks.
Yeah. Okay, so all these are now from our work with Kasprzak, Skalski, and Venue. I'm not going to keep mentioning our names. So we could prove that every discrete quantum group gamma admits a unique universal maximal gamma boundary, which we are going to denote it by this, in the sense that any other gamma boundary A, so these are C-star algebras on which gamma acts, could be embedded completely isometrically via gamma equivalent UCP map into this universal gamma C-star algebra, this universal gamma boundary. And we are going to call that the Furstenberg boundary of gamma. So this is a C-star algebra, and it's not, I mean, again, this is just a notation. This is a non-commutative C-star algebra in general. It's immediate from the definition, so perhaps I don't need to go a lot, but again, there is a notion of amenability for quantum groups, and triviality of this boundary actually captures or characterizes amenability of quantum groups. Okay, so let's get into the applications. The problem of uniqueness of trace, we could prove the following general result, that if I have a faithful boundary action, well, that is equivalent to say that the action on the universal boundary is faithful. Suppose that that's the case, that the action on the Furstenberg boundary is faithful, then if gamma is unimodular, which I remind you that the same as saying that the Haar state on the dual is a trace, then that trace is the unique trace on the C-star algebra of the dual, which I'm going to denote by C-star reduced of gamma, obviously. And if it is not unimodular, in which case the C-star reduced, the Haar state is not a trace, then this C-star reduced does not admit any gamma invariant functional, nor any KMS state for this scaling automorphism group. Sorry, now I'm just mentioning things that I didn't introduce, but perhaps I could skip this and we just take the result in the unimodular case. So this gives a way to prove uniqueness of trace on the reduced C-star algebra of a discrete quantum group. by examining the faithfulness of the Furstenberg boundary action. Now, on the C-star simplicity problem, we could prove the following are equivalent. The reduced C-star algebra of discrete quantum group is simple if and only if the reduced cross product with any gamma boundary is simple, if and only if the reduced cross product with some gamma boundary is simple, and that's all. Those are all equivalent to the reduced cross product with the Furstenberg boundary to be simple. So these are general results, which at the end I'm going to apply them to concrete cases and show that these are really useful and give new results. So also we prove the following general result that a characterization of gamma boundaries for any discrete quantum group gamma is the following. A is a gamma boundary if and only if the reduced cross product would embed inside the injective envelope of the reduced group C-star algebra. So in particular, if this is a nuclear C-star algebra, of course, by construction, it contains the reduced C-star algebra, which then would be exact. And in that case, Ozawa's conjecture would hold for this exact C-star algebra, because then you do have a nuclear one that sits in between. Okay, but then, of course, so these are quite nice and general, but then always the problem in quantum cases, then what? What are the examples? So I realize that I'm running out of time, so I'll finish by applying to concrete examples. But the problem is how to find examples in the quantum case of boundary actions. So classically, in the group case, almost all the boundary actions that are shown to be boundary actions are obtained by using hyperbolic or parabolic type homeomorphisms or elements in the group that is acting. So these are the ones that so this is a very specific orbital behavior. So they would send all the points to a fixed point, and so then that allows you to use certain bounded convergence or whatnot to show that they have to also send every probability to a delta measure. But I mean, whatever this is a very point wise orbital behavior, and this is I mean, you can feel that these are not really quantum friendly, so you cannot really translate this nicely into quantum setup. So we had to come up with other ways of characterizing or proving something is a boundary action. And this is the main theorem in this setup. So given a discrete quantum, so this is at least one condition that ensures a gamma C-star algebra is a gamma boundary. Given a discrete quantum group and the normal state on its von Neumann algebra, suppose that you have a unital gamma C-star algebra A that admits a unique mu stationary state. What that means, it means that nu is a mu. If I convolve mu with nu, I get nu back. So nu is invariant under convolution by mu. And such that, this map, which I should tell you, this is the non-commutative version of the Poisson transform I defined for groups acting on sets earlier. So this transforms elements in A to elements in L infinity, the von Neumann algebra of gamma, in the most natural way. So if this is completely isometric, then gamma will be then A will be a gamma boundary. And again, so state is mu stationary if it is fixed under convolution by mu. Okay, so now we could really apply all of that to concrete examples. One of the most studied and most important examples of discrete quantum groups are the so-called free orthogonal discrete quantum groups introduced by Van Dale and Wang. And I'm not going to go into the details of how this is constructed, or at least I tell you how. So for any natural number bigger than or equal to 3, take a matrix, n by n matrix. Here Q bar is thus doing all the components of Q, the matrix Q, just do complex conjugate of them. Take a matrix Q as this. And so there is a quantum group defines, so this discrete quantum group is defined to be the dual of the following compact quantum group, which is defined as follows. The C-star algebra, well, this is not the reduced one, but this is rather the universal C-star algebra. The full C-star algebra is defined to be the universal C-star algebra generated by n squared elements uij, such that when I put them in a matrix, they become a unitary matrix in n by n matrices on this C-star algebra. And it satisfies the following condition. Never mind. And the coproduct is the unique extension of this map to this C-star algebra. So there is a theorem to show that this indeed gives you a compact quantum group. And now we're looking at its dual. And this is very much well studied. So these are considered as to be, in many senses, the quantum versions of the free groups. So in this sense, actually, Wass and Vernieu defined a Gromov boundary for these quantum groups. And they proved that this Gromov boundary satisfies a lot of properties similar to the boundary of the free group. So what we managed to prove was that a canonical state on, so this is a gamma C-star algebra, by the way, by definition, this Gromov boundary. There is a canonical state, I'm calling it a Poisson state for a certain reason. And that state is a unique stationary state on this C-star algebra. Stationary with respect again to a canonical normal linear functional on an infinity of the discrete quantum group. So this does satisfy, this suddenly fits into our theorem that I just mentioned, which allows us to identify boundaries. So as a corollary to this statement, so this is rather not easy to prove, but as a corollary, suddenly we get that the Gromov boundary that they defined is a gamma boundary in our sense. The second is that Ozawa's conjecture holds for the reduced C-star algebras of these quantum groups. Actually, Wass and Vernieu proved in their paper that the reduced cross product with this Gromov boundary is a nuclear C-star algebra. So then suddenly it fits to our general results earlier. And then we proved that we also can conclude from this statement that these are boundaries, that the reduced cross product with these boundaries are going to be simple under a certain assumption. Wass and Vernieu proved that these quantum groups are sister simple under this condition. And as I said, we can, because these are gamma boundaries, simplicity of this would translate to simplicity of these cross products. And this is rather new and only achieved via this boundary theory, I should say. And on the last question, we also we could prove that the action of these quantum groups on the Gromov boundary is faithful, but this is also a gamma boundary in our sense, which tells us that in the case that this gamma is unimodular, which is exactly when the matrix Q that I started with to construct these quantum groups is unitary. In that case, this is unimodular, so the Hart state is a trace, and that is the unique trace. And otherwise, it does not have any KMS state for, again, scaling automorphism. And I apologize, I didn't introduce what this is, but I mean, if somebody is interested, I can tell later. But perhaps I should stop here.
Thank you very much.
Of course.
So it was very interesting talk. Any question?
Oh, yeah, we have. Go.
Mehrdad, I'm just wondering, so you mentioned CATS type earlier on. How much did you have to assume that it's a CATS type for this to work?
Sorry, I didn't hear again. How much?
You mentioned CATS type earlier on. Is CATS type, it's not essential for this, for the definition of the first boundary to work.
Somehow I don't hear the end of your question, but so these, if you're asking about these examples, so these will be CATS. Yeah. So for instance, when Q, the matrix that I start with to construct them, if it's a unitary matrix and by a complex matrix, then what you get is a CAT type quantum group. In which case, then then the Hall state is a trace, and then we have the unique trace result.
But there's no assumption in your the results, the general results, that the locally compact one, discrete quantum.
No. That's that's a good point. So no, the general results all work in general quantum group setting. So the only place that CATs come into the game is whether you have a trace or you don't have a trace on the C-star algebra of the dual. Yes, but the general results are there.
Okay, so then that leads to my second question. If you try to do this for quantum SU2,
yeah,
what have you had it? Have you looked at this, or to try to construct?
Right. So quantum SU2 falls into this, and so it's one of. Okay. So I don't think we say anything that was not known already, but. Okay, so what we can say actually perhaps that is new in those cases. Okay, I should say that was when you already knew that the reduced C-star algebras of all these quantum groups are simple, and in the case of CATs, they have unique trace, and in the non-CATs case, including quantum SU2, they prove that they do not admit any KMS state for the modular automorphism group. So for the automorphism group that tells you the difference between left and right Howard. What we got, which came somehow surprising out of nowhere, so we proved that in those cases there is no KMS state for the scaling automorphism group. So this is the scale for everybody else. This is the automorphism group that tells you how much the quantum version of the inverse of a group is bounded or unbounded, let's say. So one thing that I skipped in the definition, I told you the inverse is an issue. It turns out that the quantum version of the inverse operation of a group is not going to be a nice morphism. In general, it's an unbounded operator on these C-star algebras and fundamental algebras. And there is a scaling, there is an automorphism group that rather scales how, I mean, this unboundedness. In some sense, I'm just making it too naive. But this is perhaps one thing that we could say about a non-CATs like SUQ, where was not known from was venue.
Okay, great. Thank you very much.
Okay, there's some questions in the chat.
Okay.
Access to chat, or I should read for you?
No, I can now see. Is there any hope for similar results like characterizations as in terms of the Furstenberg for locally? Oh, that's a good question. Not exactly the same, but there has been some work on the non-discrete case. You understand that, so first of all, if I have a connected group, then, well, it's not C-star simple. So in that case, you see, there's not much to talk. But actually, the question really remains for totally disconnected groups. Is there a characterization? That's a very interesting question, not known. People have worked on it. We don't know. And so a lot of what I told you about here, a lot of this theory works. So the compact, so the unitality is quite present. And the fact that the reduced group C-star algebra of a discrete group is unital, and then you go to non-discrete non-unital, that's a huge, I mean, that more or less most of these statements fall apart, I should say. So short answer, there is a hope. Yeah, I mean, well, maybe somebody could, some even can conjecture that, but we don't know. There are some partial results. Earlier messages, okay, so sorry, I'm just going back. Sure. What about the full cross product of B infinity with gamma? So they prove Wasfer knew that the action is amenable, topologically amenable again. So this is a very technical quantum version of topological amenability of the action in the discrete group case. So it turns out that the full cross product is the same as the reduced cross product in this case, B infinity with gamma, if you meant these particular examples. Oh no, of course.
Okay, so any other question?
Yeah, so well, I'm not sure if you mentioned it, and maybe I have missed it, but so in the classical case, sometimes instead of the boundary action, you can work with these actions on minimal convex sets, right? The affine actions, and that also gives a description of all possible boundary actions, right? So so do you have something similar in the quantum case, like quantum compact convex spaces?
So that's an interesting question. Actually, I guess I formulated something like that, and I put it as a question in one of my grant applications, and but I haven't looked at it. So here's what you can do. You see, as you say, another way to construct the Furstenberg boundary is the following. So given a discrete group, you can look at all compact convex spaces on which this acts, and then there's a notion of irreducibility, and then irreducible ones correspond to, say, probabilities on these boundaries, and then among them you can construct a universal one, which would be the probabilities on the Furstenberg boundary. So there's a way to construct probabilities on the Furstenberg boundary in the language of convex gamma spaces. Okay, so now you in that construction, in the discrete group case, you can realize that when gamma acts on a compact convex space, then L1 of gamma also acts then. Actually, probabilities, I should say, probabilities of gamma acts on that naturally. And then you can consider the semi-group of probabilities of gamma, and then do a construction like this. Construct a Furstenberg boundary for a given semi-group. Just look at the actions in the natural way on convex spaces, and then irreducibility is defined naturally, and then do the universal one. And then you get the same. It doesn't. So, but now I come to quantum case. When gamma discrete quantum group acts on the unital C-star algebra, I mentioned earlier that allows for normal states on the ad infinity of the quantum group, so say quantum probabilities on the discrete quantum group to act. So this is again a semi-group indeed, and it acts on the state space of the unital C-star algebra. And so so you can do the following. You can start from a discrete quantum group, consider this semi-group of all quantum probabilities on this, and then construct a Furstenberg boundary for a semi-group. I mean, that does not exist in print anywhere, but it's the same construction. There's nothing into it. And then you're going to get indeed a universal object, the Furstenberg boundary of this semigroup. And I don't know, so it would be larger at least than the, I should say, then the status space of the Furstenberg boundary, non-committed Furstenberg boundary, will be a boundary in that sense. It will be a factor of that universal convex space. I don't know, probably it's not the same. And it's interesting. So this will allow us to translate everything into really actions of semigroups on compact spaces and become classical. I haven't really looked at it. It seems quite interesting. Usually, there should be something you can prove in one direction, not the other direction, but still in one direction is still nice enough.
Okay, thanks.
Yeah.
Okay, any other question? Okay, thank you very much, Mehrdad, for a nice talk. Hope to see you again.
Yeah, thank you all.
Okay, so
Bye.
see you. Bye.
Bye.
Oh, but okay, maybe before this, Karen usually announced the seminar for the next week. But Karen, you are mute. We cannot see you. And we cannot hear you.
Yeah, Ken, okay, I'll announce it. So next week's talk is Volodymyr Mazurchuk from Uppsala University, and he will speak about bi-Grassmannian permutations and Verma modules. So we hope to see you all there.
Okay.